Welcome to 16.8, the second to last video of chapter 16, or of Calc 3, and that is Stokes' theorem. When we look at Stokes' theorem today, we're actually going to be looking at the connection between a line integral and a surface integral. And we're going to return to one of the first objectives that we looked at with line integrals, and that is evaluating work. So let's just jump right in. Starting with a recollection, let's recall if we have the line integral of f dot dr, and remember that this little figure here lets us know that we have a line integral that has a closed curve and that it has a positive orientation. And if we remember, we could rewrite this as the double integral over the region R of the partial of q with respect to x, subtract the partial of p with respect to y dA. And that is Green's theorem. And if you remember, Green's theorem applies to closed curves on the xy plane. And then we talked about rewriting Green's theorem as the double integral over the region R. And if you remember, we could write this as the curl of f dotted with k dA. And now for just a quick reminder, why were we able to do that? Well, if we write the curl of f, so curl is the partial with respect to x, partial with respect to y, partial with respect to z, and then we have p, q, 0. Oh, I went out of order. I, j, k, and p, q, 0. P is a function of x and y, q is a function of x and y, and then z is 0. And that's because Green's theorem applies to curves on the xy plane. And so when we calculate that, we get, if you remember, 0, 0, the partial of q with respect to x, subtract the partial of p with respect to y. And then if we dot that with k, our 0, 0, 1, we get back to the expression in our double integral. All right, so curl of f dot k will get us this quantity above. So when we first learned curl and divergence, we saw that Green's theorem could be tied to curl. Well, so now what we're going to look at is we're no longer just on the xy plane, we're going to be looking in 3 space. As a reminder, before we write down Stokes' theorem, let's review the right-hand rule. The right-hand rule says if you're this person right here walking around the surface should be on your left, and that will give you the positive orientation. So as you can see with this person walking, the surface is on the person's left. So up then is the positive orientation denoted by n being the unit normal vector. And remember, we talked about previously with positive orientation that n is never going to abruptly change directions. So we're never all of a sudden going to be going down for n. So finally, let's look at Stokes' theorem. So Stokes' theorem says, let S be an oriented, piecewise smooth surface bounded by a curve C with positive orientation. Then the line integral of f dot dr, so remember, this is calculating work, that can be written as a surface integral of curl of f dot ds. So let's see Stokes' theorem in action. Example 1, we have f, which is that vector field. Find the work done by f on a particle transversing the plane z equals y as shown. Okay, so the first thing I would do when I see this problem is I would set up my integral. Work, so I know I'm doing a line integral of f dot dr. Okay, so let's just ignore Stokes' theorem for a minute and think before coming into this video, how would we have calculated f dot dr, or how would we have calculated work? So previously, we might have thought of using Green's theorem. So we could use Green's theorem if the curve was on the xy plane, which we can see that's not the case, right? The particle is transversing this way on that purple plane. So we couldn't use Green's theorem in this case because our curve is not on the xy plane. Or we could have parameterized those 4 lines separately and set up 4 line integrals. So that's what we would have had to do here. We would have had to set up a line integral for this line, a line integral for this line, a line integral for this line, and then a line integral for the last one. So that would give us a line integral for the first curve of f dot dr, add line integral for the second curve of f dot dr, so on and so forth. So as we can see, that would be highly inefficient. We don't want to have to calculate 4 different line integrals unless we have to. Okay, so now that we see that that is not going to be efficient, this would be a case where we would say, can we use Stokes' theorem? Here's the questions to ask. First of all, is our surface smooth? Yes, it is. Second one, do we have a curve with positive orientation? Considering the orientation, we have 2 different options. So if this is our curve C, like we said, this purple outline, we can picture n going up or n could be going down. If n is going up, so we have a person standing here straight up walking around the curve, we see that the surface would be to that person's right, not that person's left. So that would give us a negative orientation. So in order to have a positive orientation, we can make that occur if n is going down. So if our orientation is this way, then we have a positive orientation. So if you, we'll get back to that in a minute when it becomes applicable, but in this case, we have our 2 necessities met in order to use Stokes' theorem. So what we can do then, instead of doing f dot dr, we can calculate this as the surface integral of curl of f dot ds. So let's start with that curl of f. So I have my ijk, I have partial with respect to x, partial with respect to y, partial with respect to z, and then the components, which is x squared, 4xy cubed, and xy squared. So I will tell you that the curl of f ends up being 2xy, negative y squared, and 4y cubed. So then the question is, what is this ds part? Well, this we've seen in a previous video, and it has to do with that orientation. So if you remember, n being down, we're going to have 3 components. That means the last one is negative. So the first 2 are the partial of z with respect to x, partial of z with respect to y, and that comes from our surface, this plane above z equals y. So that then ends up being 0, 1, negative 1. Okay, so finally, we are ready to actually calculate work. So our work ends up being double integral over the region R of that 2xy, negative y squared, 4y cubed, dotted with 0, 1, negative 1, dA. So this is the double integral then of negative y squared, subtract 4y cubed. And then as we can see on the figure, R, which is just the reflection on the xy plane, is a rectangle, which is so nice. So if I integrate with respect to y first and then x, y goes from 0 to 3, x goes from 0 to 1. I think we can agree that this work using Stokes' theorem is going to be significantly more efficient than setting up 4 separate line integrals. Now, I'm not actually going to do the integration because that's not really the point of this video, but I will tell you if you want to do it on your own, you get negative 90. Okay, let's see another example. Example number 2, evaluate f dot dr, where f is that vector field and c is the curve of the intersection of y plus z equals 2 and x squared plus y squared equals 1. Orient c to be counterclockwise when viewed from above. Okay, so first thing that I want to note, I have not said these in the other videos, and so I want to make sure that I say this now. I am giving us these figures so that we don't have to spend time drawing them. You will need, though, to know what y plus z equals 2 and x squared plus y squared equals 1 looks like. So on a test, let's say, or in your homework, you're not going to be given a figure. So you will need to draw that figure and draw it accurately in order to guide your work. Okay, so knowing that, if we look to evaluate this f dot dr, like we thought of on the previous question, we can't use Green's theorem because our curve is not on the xy plane. We could try to parameterize this curve. That's going to be a little bit of work though. We would have to find the intersection of our plane and our cylinder. So at this point, using a line integral might be a little bit of work, or it's going to be a little bit of work. So this is where we would think, is Stokes' theorem going to be helpful? So first question, like we asked before, is our surface smooth? Yes, it is. Does our curve C have positive orientation? Okay, well, let's take a look. We have the arrows here because we're going counterclockwise this way on C. So if we picture a person standing straight up, walking around, we see that the surface is on the person's left. So yes, that's true if n is going up. So because both of those are met, we can use Stokes' theorem, which is helpful. Okay, so we're going to start like we did before by finding curl of f. So I have my ijk, partial with respect to x, partial with respect to y, partial with respect to z. And then our components are negative y squared, x, and z squared. So curl ends up being 0, 0, 1, add 2y. So then we're also going to need to figure out our n. So that is going to come from this plane. So we're going to have to solve for z. We get z equals 2 subtract y. So then since our n is up, like before, last number is positive, so then we're going to get negative zx, negative zy. So this gives us 0, 1, 1. Okay, so now the line integral of f dot dr is the double integral over the region, I'm going to use d in this case because that's what is on the figure, of 0, 0, 1 at 2y, dotted with 0, 1, 1 dA. So this becomes double integral of 1 add 2y dA over the region D. And now, as we can see, this region D is a circle, so that of course suggests to us that swapping a polar might be a better option for us. So when we do that, we get 1 add 2 r sine of theta times r dr d theta. R goes from 0 to 1, theta goes from 0 to 2 pi. And again, I'm not actually going to integrate this because that's not the focus of this video, but if you do decide to integrate, you will get an answer of pi. So now that we've seen Stokes' theorem in action in two different examples, we're going to return for a quick minute or two to the connection between Green's theorem and Stokes' theorem. Okay, so if we look at Green's theorem again, Green's theorem f dot dr, we said we can write as the partial of q with respect to x, subtract the partial of p with respect to y dA. Well, the connection here is that Green's theorem is just a special case of Stokes' theorem. It's just a special case of Stokes' theorem. We actually showed that in the beginning of the video, and it's the special case where your surface is on the xy plane. So that's it. I guess that's all you need to know. That was pretty quick. What we're going to do, though, is we are going to, in example 3, actually verify Stokes' theorem for this f, where s is the figure, oh, you're missing something, so add this in, where s is z equals 4 minus x squared minus y squared, with z is greater than or equal to 0. Upward orientation, and c is the curve x squared plus y squared equals 4 on the xy plane. So first thing we're going to do is we don't have a figure, so we're going to draw a figure. Hopefully we remember what a lot of these look like. Okay, so one thing we have is this x squared plus y squared equals 4 on the xy plane. So of course that's going to be a circle with a radius of 2. So that is our curve C. And then we also have this z equals 4 minus x squared minus y squared. And that is a paraboloid. So that is our curve S. And we said that there is upward orientation. So here is our orientation. And then we also have that C on the xy plane is positively oriented. Forgot that part. Positively oriented, so our surface is on the left. Okay, so if we're verifying Stokes' theorem, it's probably a good idea just for us to write that down. So we have the line integral of f dot dr can be calculated as the surface integral of curl of f dot ds. So ultimately, we're going to have to calculate both of these. So step 1, we're going to calculate the line integral of f dot dr. And so that is for that curve C. So what we are going to do is we are going to parameterize that curve. So that can be written as 2 cosine of t, comma 2 sine of t, comma 0. So then that line integral can be written as the integral of f of r of t dotted with r prime of t dt. So if we do that using our f from above, so this f, 2z is going to give us 0, 3x is going to give us 6 cosine of t, and then 5y will give us 10 sine of t. And we're going to dot that with r prime, which is negative 2 sine of t, 2 cosine of t, and 0 dt. This gives us the integral of 12 cosine squared of t dt. And t, being our parameter, goes from 0 to 2 pi. And I'm just going to tell you that that ends up being 12 pi. So now what we're going to do is we're going to calculate this again using the surface integral of curl of f dot ds. And remember, we know that these should be equal because we have a smooth surface that has a positive orientation. So we know that when we calculate f dot dr, or the surface integral of curl of f dot ds, by Stokes' theorem, we should get the same value. So let's start like we have on all the other ones by calculating curl of f. Partial with respect to x, partial with respect to y, partial with respect to z of 2z, 3x, and 5y. I'm not going to focus on that calculation. If you trust me, you should get 5, 2, 3. And then we know that S has upward orientation. Which means when we do our vector, last number is going to be positive, and we have negative z of x, negative z of y. And our z coming from our paraboloid. So that would be 2x, 2y, 1. So then, when we have our surface integral of curl of f dot ds, oh man, I really did not use my space wisely here. That's going to be double integral over the region R of 5, 2, 3, dotted with 2x, 2y, 1. So what I'm going to do is just move my screen a little bit so I can continue my calculation. So that becomes double integral over the region R of 10x, add 4y, add 3, dA. And we can probably see, since our region R is a circle, that converting to polar is the way to go. So when we do, that would give us 10r cosine theta, add 4r sine theta, add 3r dr d theta. R goes from 0 to 2, theta goes from 0 to 2 pi. And again, I'm not going to actually calculate it for you, but I will tell you, you get 12 pi. So sorry that my work is a little all over the place, but what we were supposed to see here is that when we calculated the line integral, like we did here, and then we did the surface integral, we got the same value. So the difficulty here in your homework or on a test is that you're going to have to be able to figure out which one is more efficient. So if I ask you to calculate work, you're going to have to be able to look and determine, is it going to be more efficient to do a line integral, or is it going to be more efficient to do a surface integral? Now, of course, either one is going to work, but one is probably going to be faster than the other. Okay, so we're going to see that in practice in the next example, which is the last example. Okay, last example. Find the surface integral of curl of f dot ds for f is as following. S is the part of the sphere x squared plus y squared plus z squared equals 4 that lies inside x squared plus y squared equals 1 above the xy plane. First thing, of course, that is going to be helpful here is to draw a figure. So that's what I'm going to start with. Okay, so first thing we know is we have this sphere, x squared plus y squared plus z squared equals 4. So I'm just going to draw it two-dimensionally, but of course we know that it's also going to come this way. Okay, the next thing that we know is we are looking inside this cylinder above the xy plane. So that would be here, going up. We know specifically that we're looking at the part of the sphere that lies inside the cylinder. So the part of the sphere that lies inside the cylinder, which is going to be up at the top right here. Okay, so that part right here is going to be our S. So at this point, what we should be thinking is, am I going to calculate this as a surface integral using this surface S, or is it going to be easier as a line integral? If I start with doing this as a line integral because it's written as a line integral, curl of f dot ds, I'm going to need to find n. That is not going to be easy. Even if I know if n goes up or down, which I can figure out, I would have to take this sphere, solve for z, and then take some derivatives. I don't really want to deal with a square root, so that might not be the best idea. So at this point, I'm thinking, do I want to do this as a line integral? If I do this as a line integral, I'm going to need to find c. So I need to find the actual curve we're talking about. So I'm going to start with the sphere, x squared plus y squared plus z squared equals 4. And that intersects with our cylinder, x squared plus y squared equals 1. So if I take that x squared plus y squared equals 1 and put it in, I'm going to get 1 add z squared equals 4. So z is equal to plus or minus root 3. But we're looking above the xy plane where z is positive. So z is equal to root 3. So our surface then is x squared, not our surface, our curve is x squared plus y squared equals 1 at a height of z equals root 3. Okay, this is pretty easy to parameterize, which verifies for us that computing this quantity as a line integral is definitely going to be easier. So we are going to do f dot dr instead. First thing, or next thing I'm going to need to do is parameterize this. So I get cosine of t, comma sine of t, comma root 3. So then r prime of t is going to be negative sine of t, cosine of t, 0. So then my line integral of f dot dr is going to become an integral. T is from z between 0 and 2 pi. If I do f of r, so I put this r into my vector field f, that's going to give me root 3 cosine t, root 3 sine of t, cosine t sine t, dotted with negative sine of t, cosine of t, 0, dt. And when I multiply all of that out, I get negative root 3 cosine t sine t, add root 3 sine t cosine t, dt, which is so convenient because those subtract out to be 0, so we get a final answer of just 0. So this is a great example of what you're going to see in your homework. You might be asked for a surface integral of curl of f dot ds, but to decide that, a line integral is easier. Now, could you have done this as a surface integral? Of course. I just didn't want to have to deal with finding z and then finding partial derivatives. Or it might be the other direction. You might be asked for a line integral, and you decide to do a surface integral. So that was Stokes' theorem. We have one last video covering divergence theorem, which will be more surface integrals. I'll see you next time.